So we're recording it.
Okay.
Yeah, we're very happy to have Sridip Pal. We're happy that we'll be short with it. He's going to tell us about universality and microcanonical entropy at large.
Thank you very much. It's always been a pleasure to be in Bengaluru and in ICTS. So today I'll be talking about universality in microcanonical entropy at large spin. So I'll be mostly focusing on conformal field theories, and as we all know, oftentimes it happens that because of symmetry and a lot of consistency condition, there are various physical observables in conformal field theory are universal. It basically means that even though I do not know all the intricate details of the Hamiltonian, if you hand me some small few parameters, I can be able to predict various kind of physical quantities like entropy, density of states, and so on. So today I will show you that in some appropriate class of conformal field theories in the large spin sector, the microcanonical entropy is universal. So this talk will be Okay, it's working. Yeah. So this talk will be based on this paper we put out last week with Jiaxin Zhao, who is at EPFL now, and Bart van Ries, who is in Paris in École Polytechnique. So the talk will be mostly based on this paper, but as I will proceed, I will also show you some results from earlier papers which led to this result. So let us begin. So suppose I hand you a quantum system. What is the most basic yet powerful question that you can ask about this quantum system? And the answer is simple, that you basically want to know about the spectra of the Hamiltonian. Because if you know that if you're super powerful, that if you can diagonalize the Hamiltonian, basically you know everything about the quantum system. But in practice, if you have a strongly coupled quantum field theory, it's very hard to diagonalize Hamiltonian. So instead of directly diagonalizing Hamiltonian, we want to understand various features of the Hamiltonian or various features of the spectra of the Hamiltonian. So in particular, today we will be asking that given a quantum system, what do the asymptotic spectra of the Hamiltonian look like? By asymptotic, I mean large energy or large speed. So in particular, suppose these are my energy levels. You can ask how the energy levels behave. What is the average density of states? Whether the spacing increases as you go up in the energy, whether the spacing is regular, or whether the spacing goes to zero. So you can ask various sort of question about these asymptotic features of this Hamiltonian, the asymptotic features of the spectra of the Hamiltonian. And this is physically interesting because it provides you some deep insight about how the system will behave when you heat it up. So for example, this, as I said here, the asymptotic spectra of a quantum Hamiltonian reveals deep insights about thermodynamic properties at high temperature. You can imagine that if you are heating up the system, as you heat more and more, you are basically accessing higher and higher energy. And that basically means that if I know something about this high energy density of states, I can also predict various thermodynamic properties. In the same way, we can also talk about thermalization at the level of subsystem if we know about this asymptotic behavior of the spectra. And we can also talk about the nature of the dynamics. For example, depending on whether the spacing shows some RMT-like features or not, I can tell you whether the system is chaotic or integrable. So the main lesson from this is that this question is important, and this question has a lot of important physics insights inside it. And today we are but in general, asking this question for a random quantum system is hard. So we will be focusing on this conformal field theory. You can think of, as we all know, that conformal field theory are like lampposts in the space of all quantum field theories, and it appears everywhere, almost string theory, condensed matter, whenever you have a phase transition where the correlation length diverges, you have some CFT. So understanding this question in the context of CFT is important, and by answering this question on the CFT, you will basically explore a large swath of physics. And there is also a technical advantage about answering this question in the context of conformal field theory, that oftentimes the CFT observables satisfy various non-perturbative, and I stress non-perturbative, consistency conditions like crossing, modular invariance, and and various kind of constraints coming from the symmetry and so on. So that means I can use this technique called conformal bootstrap analytically or numerically to translate these non-perturbative consistency conditions into some constraints on the observable. So the observable become highly constrained. So we are going to use this sort of mechanism in analytic form today to answer this question that what do the asymptotic spectra of the Hamiltonian look like in the context of conformal field theory? Yes. Yes. Mm-hmm.
They will also contribute equally, right?
What do you mean by equally?
The time states they occupy.
Yes, but then their weightages are different. So another way of saying this, you will see. So I guess you are thinking of this e power minus beta h factor, and as beta goes to 0, everything is equally weighted. But you will see that at the higher energy, there are lots of states. So the degeneracy kicks in, and this degeneracy will win over. So in that sense, you will see it precisely how it happens. Yeah. Okay, very good. Please feel free to ask any questions. And so today the question we will ask is that given a conformal field theory, what do the asymptotic spectra of the Hamiltonian look like? And the ADS CFT gives you another layer of motivation to this question, that why do you care about this question? So the asymptotic spectra, the ADS CFT teaches us that the high energy states in CFT are dual to some black holes. So the asymptotic spectra of a CFT provides insight into quantum nature of black holes. For example, you can ask about, so the idea is in a holographic CFT, you compute the high energy density of states, you compute the entropy, and then you can relate it to the area of the black hole, and which is related to the entropy of the black holes. In the same way, the physics of near extremal black hole is captured by some CFT operators with large spin, low twist, and you can ask all sorts of questions. For example, in a gravitational path integral for various parameters, when does a black hole dominate? And answer to all these questions in some sense is hidden in studying the high energy states in conformal field theory. So that provides another layer of motivation. So and generally when we talk about this kind of setup, we take central charge to infinity, which is a parameter in the CFT side. So today I will not be talking about holographic CFTs, but you should keep in mind that whatever result I show you today, there should be an analogous result in this holographic setting, which would say something about the black holes. So that's another motivating factor behind studying these kind of questions. So moving on, so the first question, as I said, that given a conformal field theory, how does it look like? So you all know about this famous Cardy formula, which came out in 1989, which basically says that irrespective of what kind of 1 plus 1 DCFT you're looking at, if you give me this single parameter, which we call central charge, which comes with the Virasoro algebra, the density of states is given by this very nice formula, which is universal, and it is controlled by a single parameter C. And this formula is true in the delta going to infinity limit. You should think of delta as a proxy for energy. To be precise, energy is delta minus C over 12. And similarly, you can derive similar formula which exists for higher dimension, coming from this paper by Loga, Siraj, Shantini, and Lahiri. And recently there is a reincarnation of this kind of technique in this paper by Nathan, Jeha, Hiroshi, and David Simmons-Duffin. But all these kinds of formula, if you look at these kinds of formula, you will see that there is a feature like this, that you write some density of states, which is some discrete distribution, and you approximate with some smooth function. So another way of saying this is that the Cardy-like formula is a continuous approximation of a distribution. But then, first of all, like if you are mathematically minded, then this equation will make you crazy, because on this side you have a density of states, which is a discrete set of states, is a distribution. On this side you have a smooth function. How does it even make sense? What does this sign even mean? And if you're a physicist, then you can refine this question, and you can say that this Cardy-like formula cannot distinguish between all these scenarios. Like it only says some statement about average density of states, but it cannot tell you whether their spacing grows like as we go up, whether the spacing is regular, or whether the spacing goes to 0. So we want to basically dig deeper into this problem, and we want to understand between these scenarios, because remember, if we want to know about chaos or whether the system is integrable, we need to know about this refined information, whether how the spacing goes. So we refine this question, and as I said, we would like to refine answer to this question when we want to ask in what sense Cardy formula is true, how much averaging do we need, and by answering this question, we would not only make the Cardy formula rigorous, we will also answer this question about spacing. Is there any question at this point? Okay, good. Okay. So a natural premise to answer this question is 2D CFT or 1 plus 1 D CFT, so which I will focus on. So here are my assumptions, which I will set from the beginning, that central charge is bigger than 1. So oftentimes I will use this symbol A, which is C minus 1 over 24, which is greater than 0. I will only talk about unitary CFTs. So when you expand the partition function in terms of Boltzmann factors, all the coefficients are positive definite. I will assume modular invariance, which basically saying that if you are putting a CFT on a torus, then the torus has a modular invariance and the partition function is invariant under something called modular group. And I also assume it's a compact CFT, so the vacuum exists and all the spectrums are discrete. At least there is a vacuum and then there is a gap. And rest of the spectrum, I do not really care, either it can be continuous or it can be discrete, but the results I will show you is only non-trivial when the spectrum is discrete. So you're thinking about a compact CFT. Okay. So this is the idea that, as I told you, that you take the density of states, and a proper way to interpret this formula is to integrate against some window function. And so you integrate the actual density of states against some window function. So this is this. So if you integrate this, that basically counts the number of states inside this window. So you see that the center of the window is centered at delta, and the size of the window is little delta. And the idea is we will keep the little delta fixed and take the capital delta to infinity. And the idea will be to show that this number of counts of states as the capital delta goes to infinity is somehow related to this average density, which is given by this function rho 0 delta derived by Cardy. So when we do this, so there are a bunch of papers that came out, and all these calculations here led to this inequality, which I am showing you. And so let me parse this inequality for you so that you can gain some intuition. So here, for example, here you can forget about the lim sup and lim in for a moment, that's technical things. So you can just treat them as a limit. So in the numerator, you basically integrate the density of states against the window. So that's like counts the number of states. And in the denominator, you have the average density, which is rho 0 delta. And then you take delta going to infinity. So roughly speaking, this is the count versus the average. So roughly you would expect that the typical size would be the size of the window. And the size of the window is twice delta. So by doing a rigorous analysis, you can show that this intuition is correct. In fact, it is upper bounded by twice delta, which is the size of the window plus 1. And it is lower bounded by twice delta minus 1. So once you have this rigorous inequality, you can immediately say something about the spacing. So let me show you how. So you have this inequality, as I told you. So now look at the lower bound. So in the lower bound, you see that if I pick my window size twice delta, twice little delta, bigger than 1, this number is positive. And whenever this number is positive, that means this ratio has to be positive. And that means the numerator has to have at least a state. So that immediately means that as the capital delta goes to infinity, if I choose a size of the window which is slightly bigger than 1, it always has some state. And that immediately means that the spacing between two consecutive states, as you take n going to infinity, this spacing is less than equals 1. So this was initially conjectured by this paper by Bauer and Sasha, and then we proved it in the next month, and yet another proof came in this other paper that came in 2020. So the upshot is that it tells you that the model, just by modular invariance, you can say that there doesn't exist any unitary modular invariant 2D CFT with sparser asymptotic spectra. And here, one more comment that here I didn't really distinguish between the Virasoro primaries and the Virasoro descendants. So you should read this formula as a formula for the Virasoro primaries and only.
Much less than 1.
Yes, that's a very important question, and I am going towards that in the large spin sector. So I'm just setting up the stage. Yes. So exactly. So the point is, first of all, if you consider all sorts of CFTs, then you can show that 1 is optimal. You cannot do better than 1 if you consider all CFTs, because if you consider any rational conformal field theories, for example, monster CFT, then indeed all the spectra is integer spaced. So the spacing is indeed 1 and you cannot make it smaller than 1. But then we also do believe that in a chaotic CFTs, as Penta was pointing out, we should be able to improve this bound somehow. So somehow you need to input this information in that you are not looking at rational CFTs, rather you are looking at the complementary set or non-rational CFTs. So even before going that, let me pictorially show that what this means. So this basically means that the first possibility I showed you cannot happen in 1 plus 1D CFT. So there cannot be arbitrary large gaps as you go up. So this possibility is completely ruled out, which is not a gauge go from the beginning. So it could have happened that the Cardy formula is only true when you average over a very, very large window. If that were the case, then the first possibility would have been allowed. But this analysis shows you that this possibility is not at all allowed. So either it can be regular spacing, in which case our bound is optimal, like you cannot do better than 1. And now this possibility is also allowed where the spacing is much, much less than 1. And the question is, can we capture this in some certain class of CFTs? So the next question I'm going to pose is this one. Can we capture this for some class of CFTs? And presumably these CFTs will be the chaotic ones. So today's talk will be mostly focusing on this stuff, this setup, and to show that at least in some sector, not the large energy or large delta, rather in the large spin limit, indeed this kind of things happens. And the spacing indeed goes to 0 if we restrict to this class of CFTs. Now let me tell you what is this class of CFTs. Yes?
Doing something about the window size?
Yes. You mean this one?
Yeah.
Yeah.
Like
Yeah, exactly. So in this game, you always have a Cardy-like formula, which is some average density of states. Then all the effort and the mathematical rigor or whatever we are doing is all about the statement about averaging window. And the question is how small you can make the window, and still you can say that confidently that the Cardy formula is true. And indeed, for example, like if you take a monster CFT and if you take a window size to be half, then the Cardy formula is not always true because you just count 0. Okay, good. So we have all these conditions, and the other condition we are going to impose is there is no symmetry beyond Virasoro, which is sort of expected in some sense because we are looking at some chaotic CFT. So you would think that if we have more symmetry, then that would spoil things. So what would be a natural assumption? A natural assumption would be you just take a CFT and you assume there is no symmetry beyond Virasoro. Now, what does this mean in terms of spectra? In terms of spectra, it means that you have a vacuum, which is 0, 0, but there is no higher spin current of the form h, 0 or 0, h bar. So which basically means there is a twist gap in the spectra of Virasoro primaries, where, to remind you, twist is twice times minimum h, h bar, which is delta minus absolute value of j. So basically you have 0, 0, and then all the other Virasoro primaries where h, h bar, both h and h bar starts from some t gap. And t gap is strictly positive. And we are going to show that in this setup, at least in large spin limit, the spacing indeed goes to 0. So I will be showing this picture again and again. So let me just orient you guys. So you have two words, left movers and the right movers. So this is the h, this is h bar. And there are two spatial lines, c minus 1 over 24. So from the holographic perspective, this is like BTZ threshold, and here also you will see that our results qualitatively differs whether you are above this threshold or below this threshold. I will come to that. And the fixed spin lines is basically J is absolute value of H minus H bar. So this J are these shaded lines which goes like along the 45 degree. Okay, you should, I would be using this picture again and again, so you should have this picture in mind. Okay. So to recap, we consider a CFTs with central charge bigger than 1. There is unitarity, there is modular invariance, there vacuum exists. And the last condition is very, very important, twist gap in the spectrum of Virasoro primaries. This basically kills all the rational CFTs, all the CFTs we know and love. Okay. So here are the results. So the plan is first I will tell you the results, briefly explain, and then I will switch to Blackboard and sketch you the derivation depending on time, how it goes. So the results are following, that there is a universality in the large spin sector at a fixed central charge, and the large spin spectrum is dense. And how is this large spin limit is taken is basically you think of this kind of strip where you fix H and increase H bar. And as you increase H bar, your spin increases because spin is H bar minus H, absolute value. Or you can fix H bar and increase your H in this direction. Then also spin increases. And the statement is the number of operators in this strip, they have a universal growth, irrespective of the size of the window. And I will make this statement more precise and refined as we go along. So that's roughly the picture. And we can also make some statement where this strip is inside this. So since there is a symmetry between H and H bar, I will only be talking about this strip and I will forget about this. But whatever I derive along this direction, you can just swap the role of beta left and beta right to derive in the result in this direction without loss of generality. Great. And I guess 1 year back maybe, so I gave a talk where this strip was along this direction. So this was from this paper. So we had some statement about what in the holographic sense you would call near extremal black holes. But now we can make a much more refined statement and you can put the strip anywhere along this direction or this direction. Okay. Moving ahead. So let me make it more precise. So you take this strip here in some particular favorite value of H, 7, 8, 9, 10, whatever your favorite number is. And then you draw the fixed spin lines, which are like these 45-degree lines. So note, because we are thinking about bosonic CFTs, all the spins are integers. So the only operators that can exist is in the overlap region of this blue line and the green shaded region. So only this, or this. So we label them, so these black strips. And the idea is you count the number of states on this black strip, and as you go up, the J increases, and you ask how many operators are there as we go up as in this direction. And we count for every black strip. Okay. Oh, no, there are infinite many lines. I just didn't draw it, yeah. So this is like J equals 0, J equals +1, -1, and yeah, so on. Yeah. Yeah. Oh, yeah. So H minus H bars are integers. Hello, Loga. And here we are imposing bosonic CFTs. If you have fermionic CFTs, then you have to allow for half integers. But as long as there is some discreteness, you can do things that we are doing. Okay. So as I said, we want to go this way, and we want to ask whether there is any universality. So here is the precise formula. So again, let me parse it for you. So the numerator basically counts the number of states in this black strip. So this omega is basically only has a support on this green strip. And you are integrating for, so this rho j delta prime is the density of states projected onto some particular spin j. So this numerator is just as j equals 0, the numerator counts the number of states here, j equals 1 here, and you go on like this. So as you go up, you would expect that the number of states will depend on the spin as you go up, and it should also depend on where exactly you are putting this green strip, like exactly where in the h direction you are. So there should be two kinds of dependence. And you would also expect that the j dependence will blow up and the h dependence will be finite, because this h is a finite number, 7, 8, 9, whatever you choose. So this formula is kind of depicts that. So you have this number of states, actual count here. Then you divide by some growth, which is almost like Cardi-like growth. And the claim is, as you take j going to infinity, this ratio is finite, and not only finite, it is precisely given by this integral, where you integrate the h variable on this domain with this function rho 0 of h. And rho 0 of h has a precise formula, which is given by a cosine hyperbolic and some stuff, where a is c minus 1 over 24.
Omega is what?
Omega is this green strip. So omega picks up the green strip and j picks up these lines. So you have the overlap.
How do you fix this thing? H plus
Yeah, so the green strip is your choice. You can pick anywhere you like. So
you remember the intersection of the green strip and these lines, one of these lines.
yes. On this side.
Yeah, on this.
On this side, this is the integral over. So this is a single variable integral. Is the integral over this region. Yeah.
So then the integral on the left hand side, the integration is along those brown lines. Right?
Yes. On the left hand side, the integral is along these lines. Yes. Exactly. Yeah.
So j of delta is actually a sum of delta function.
Yes, exactly. Yes.
There,
Yes, exactly. The rho 0 is a smooth function. Yes. So this is a non-trivial statement that this limit actually exists and goes to a smooth function. Yeah. And also there is a theta function here, which basically tells you that this function only has a support above c minus 1 over 24. So that basically says that this limit actually goes to 0 if you take the strip below c minus 1 over 24. So that's the qualitative difference between whether you are above c minus 1 over 24 or below c minus 1 over 24. Okay. Is this slide clear? No, that step function just comes out of calculation. So later when this is not the gap. The gap is up to t gap. So that's some other number. And this A is only depends on the central charge. So this function just comes out of calculation. So but to derive this thing, you need to assume that there is a t gap. So in other words, so you may ask that why then the t gap doesn't show up in this formula if it is so important. So the point is, when you take the limit, the limit goes here, and that basically means there are error term or correction terms, which basically goes to 0 as you take the limit. And you can show that if t gap is not 0, then the error basically blows up. So that information about having a non-zero t gap is hidden in deriving this formula.
small h must always be greater than capital A.
Yes.
But it's an h are very large.
Yeah.
Minus 1.
Mm-hmm.
H,
Mm-hmm.
where you are,
Mm-hmm.
is greater than percentage.
Yes.
It's okay.
Yeah, it's okay. For example, in the holographic setting, you can say that whether the BTC threshold is C minus 1 over 24. So you are above this threshold, then basically you are probing the black holes. And then you would expect there is a Cardi-like state, Cardi-like growth. And if you're below the BTC threshold, there's no black holes. So if you would expect that this answer is 0. And indeed this happens. But the caveat is that, caveat in the sense depends on, so from a physicist perspective probably is fine, but this result is only proven for finite C and large H. The result I said about the BTC threshold, that can only be proven when you do a different kind of limit. But the hope is that if you can prove this, that thing also can be done. Yes, exactly. Yes, these are large spin black hole. Yes, yes, large spin black holes, yes.
This formula can be related to some black hole entropy formula.
Yeah. So this is basically like the extremal entropy, you can say, in some sense. And this part is the away from extremality. Well, here basically you are far away from extremality if you go far away from C minus 1 over 24.
But far away from extremality, then there is a two exponents, right?
Yes, so you can see here also exponential.
Why is it minus? The
Oh.
negative sign is
This is exponentially suppressed, so you just forget about this term. And this term is always positive because, well, one is a minus one is a. So this thing is precisely the Cardy formula. So what happened for this j part also there is this formula, but I approximated it because j goes to infinity. So ideally we did the computation and we proved it. The way to guess it is basically you think that there is a BTZ black hole, there is a Cardy formula, so you would expect there is a black hole entropy. So this is precise. So you write down a Cardy formula for h and h bar, and h bar goes to infinity, so you replace h bar with j, and then you just see this factor pops out. So that's the easy way to guess. Yes, I'm going to that. Well, correction, I can estimate the correction in some appropriate way. So I will just tell you. Yeah, that's a very natural question to ask. Yeah.
So this looks like it is still close to extremality. Going away from extremality will mean h and h bar both large. That's what you are trying to do, right?
Yeah, it depends on how you are going away from the extreme. So it could happen that you can create a hierarchy between h. So near extremality is when you are creating a hierarchy between h and h bar. So here, of course, you are creating a hierarchy between h and h bar. So in that sense, is the near extremality.
Yeah, also I'm calling it near extremality because normally if you look at non-extremal black hole, then there is square root of CL, HL, and then there is square root of CRH. Here you have only one. So you don't have two exponents. Right?
Yeah, but you see that, yes, that's true, but the other exponential is hidden here. Cosine hyperbolic goes like e power 4 pi a.
Okay.
So in that sense, so all I'm
one exponential there, where is other?
Here, yes, I just put it inside because so that I can write this precise limit j going to infinity, because otherwise I cannot use that symbol. Yeah.
And j is much larger than h. Okay.
Yes, j goes to infinity, where h is held fixed in this tree. Yeah. So I guess it's kind of an amazing thing that in 2D that you have a Cardy formula for h and h bar where both are large, and then you can extrapolate the formula all over the regime. And this doesn't happen in higher dimension. This is kind of very special in 2D. Yeah, so in some sense, Cardy formula is more right than it deserved to be in some sense. No, the only assumption that goes in h is greater than t gap. Twist gap. There is a positive twist gap. And this just comes out of analysis. There is no assumption. No. Yeah. Anything. Any number you want. You can take h to be less than a also, then just is 0. Then also is true. Okay. Secret interpretation of what? Oh, rho naught, I would think of this as a, so if you take this very near the threshold where h is near a, then I would think that all the correction from the extremality, like the things that controlled by the Schwarzian, is captured by this integral, the log of this integral basically. Yeah, there are some gravity computations by like some limit of this. So you have to then take the limit h is very near a, so then it will be a square root h. And there are computation by Anemi Ghosh, Turiachi, Luca Elisiu, and there is a concrete gravity computation to reproduce this answer. Yeah, then it becomes a polynomial. Yeah. Yes, irrational function. Yes, right. Yeah. And away from then it becomes exponential. But I think in the Schwarzian regime, it just, there are various approximations, and it depends on exactly where you are from the gravity. You can either see the square root or other things. But I must say that from the CFT side, when you take large central charge limit, the near extremal limit is a bit subtle. Then I think gravity can predict much more than what in the CFT you can rigorously prove. Yeah. Which basically means there's more to work. Is nice. Okay, good.
So I guess gravity doesn't work for every CFT, right?
Yeah, exactly. Yes, exactly. Exactly. So you need more sparseness condition or some sort of extra condition. Yes, exactly. Yeah. So the only thing is that you can slide it, but if you slide it unboundedly, it might happen that the asymptotic kicks in for later and later J. So you have to be a bit more careful. Okay, good. Yes, exactly. Yes, you're right on the track. Yes. Okay, so I already mentioned a bunch of things. So the right-hand side is non-zero irrespective of the width of the strip. So you can, so in this setup, at least as far as I am telling you right now, you can take this size of the strip, any fixed number you want, and there is a result. And this immediately tells you, because you can make this strip, the size of the strip can be anything, that immediately tells you the maximum spacing of states with a fixed spin J goes to 0 as J becomes large. So you are counting so suppose you have states here and you count the maximum spacing here, maximum spacing here, maximum spacing here, and you go up. The maximum spacing has to go to 0, because if it doesn't go to 0, then you will find a small gap, and then this equality would be violated. Yes, then that's I'm coming to that. Yes. No, it is fine. So now we have already made an improvement. Earlier I said it's less than equals 1, and then Sventa asked that how less than 1. Now I am saying it goes to 0. So in some sense I already answered Sventa, but now I haven't answered. As a function of J, how does it go to 0? So what is the J dependence? And this also tells you that the entropy is universal up to order 1 term in J, which is kind of non-trivial, because normally in the Cardy formula, whenever you write down the entropy formula, there is a square root delta term, there is a log term, and the order 1 term is always non-universal because it depends on the averaging and so on. But this formula doesn't require any averaging in J. So we are only averaging in the H variable. In the J variable, there is no averaging. And intuitively, that kind of translates to the fact that entropy is universal up to order 1 in J. And well, intuitively, you would expect that to happen, and then we basically show. And in fact, we can do much more, as I will tell you soon. Okay, so this formula, roughly speaking, is like this, that you count the number of states, there is extremal growth in the J variable, and then there is a finite number in the H variable. Now, as everyone was asking, you would ask that, well, this is the limit, but how does this limit is approached? How is this limit is approached? How does the error behave? And can we make the window size shrink? And if we can make the window size shrink as we go up, we'll probably be able to say that how does it go to 0 as J goes to infinity. Okay. So here is the more precise result. So what do we do here? So let me unpack some stuff. So I rewrite this rho j delta prime with this function rho j plus 2h. So I just rewrite this delta prime in this variable so that I can integrate over h prime. Sorry, this should be all h primes. My bad. And this rho j vac is basically this term rewritten in this form. And this function phi is some compactly supported smooth function on this domain. So earlier I was just counting the number of states, but now instead of counting it, I am doing.
Back is that extension always to J roll
Yes.
Then you are dividing it by A.
This is the leading growth basically. Yeah. So if you think little bit ahead, at the end of the day, Cardi formula comes from some vacuum term. So this is basically the inverse Laplace of the vacuum term. This is the full thing, and this is the leading growth, and I'm computing the leading error. But the important point here I want to emphasize that this earlier I just counted the operators, which basically means earlier I said phi to be some window function, but now I am doing some trick. I will choose this phi to be compactly supported, which is like the window function, but then I will also assume this is a smooth function. So this is a smooth compactly supported function, which in other words in the math literature it is called bump function, like somewhat like e power minus 1 over x square minus 1, some sort. In the variable h, yeah. It's a smooth bump function, so it's a infinite smoothing of this window function. So if you use this infinite, so it still kind of only contains information on this strip and it doesn't leak away. If you do that thing and if you smear it out, if you divide this, then the error term is j to the power minus n for any n. So the error term goes to 0 faster than any polynomial. No, it's far. 1 will work, 2 will work, 3 will work. Any integer n will work. So that's another way of saying it's faster than any polynomial. Any inverse power, yeah. Sorry, say that again. Oh, because delta is j, so h is delta plus j minus. So yeah, I think this is probably a stupid way of writing this, but because I wanted to change this integral to h prime so that to make things here also h prime. So yeah, that's why. Just a change of variable. Yeah, with this exponential. Yeah, exactly. So I'm just computing so this is the leading term, right? So I'm computing the difference and dividing by the leading growth. So this is the relative error. Yeah, so this is like the denominator is LHS minus RHS, exactly. And smoothened. And this one is this one. So you mean why there is this thing? So see, there's a LHS, this is RHS. You are doing LHS minus RHS divided by the RHS. And then you would say that why there is an integral, why I'm not writing this thing here, right? But this is an order 1 number. So whether you write it here or not write it here doesn't matter. Oh, sorry, I made a mistake here. It should be AJ. Because there is a central charge. Sorry, good catch. Yeah, because the growth is always okay. Did I make a mistake? Yeah, no, this is the AJ. I think I started making mistake from here. Okay, good catch. Someone is really listening. Yeah. Okay, good. Here, this should be A, and yeah, this is also A. Yeah. Because
instead of taking infinitely smooth, but made some say a derivative.
Then this should be just fixed that in. Yeah, exactly. Yes.
This is the case, and then you take something root and multiply it singular.
Yeah.
Its fluctuation starts.
Yes, exactly. Yes, exactly. So this is captured. Yeah, exactly. The Fourier transform has exactly as you said. Yes, that's the intuition. Yeah. But now this estimate actually helps us to do some clever estimate. In fact, once we do this, we can basically. So the problem is that earlier we cannot shrink the window as a function of j because there was a worry that maybe the error term blows up. Yeah. Mhm. No, H is only stripped. Or basically because this is a compactly supported function. Yeah. So it's compactly supported and smooth. That's why the Fourier has a like a faster than polynomial growth, polynomial fall off. How big this strip can be? Oh, at this point, well, you mean how small? How bigger is better, right? No, I'm saying that this growth is very large, but it's growing exponentially. Yes. Yes. So should you put some more counter conditions than this? No, the point is that like this size can be, so the size is fixed. You cannot grow the size with the function of j. You can string. Yes, yes, yes. So at this point, this is that. Yeah. But you can do some. Practically take j very large. Yeah, exactly. Yes, exactly. The asymptotic might kick in at the later point. Yes. But here we are interested in the reverse question, whether we can shrink the window, because we want to say how fast it can go to 0. Okay. So now it turns out that we can make the window size shrink as fast as j to the power minus 1/4 plus epsilon. So that's answer to Spencer's question. But we are not yet done. If we only show that the window size can shrink as j to the power minus 1/4 plus epsilon, that would not immediately translate to a statement about spacing. Because it might happen that on this strip, the asymptotic kicks in at j equals j star. If you go to this strip, the asymptotic kicks in at j equals 2j star. If that happens, we are again screwed, because then this result doesn't mean anything about the spacing on some particular line. So this epsilon is any positive number. So yeah, we write it this way because we have to allow for scenarios which can be j to the power minus 1/4. Exactly. Yeah. Exactly. So this is a standard way that analytic number theories use actually, this kind of thing. Okay. So as I said that this statement is not enough, and probably you can guess because I wrote this down here. So this is very important, that the estimate is locally uniform is A star, where A star is the center of the interval. So that basically means as long as you are in a bounded interval, as you tune your H star, the asymptotic kicks in at the same point. And because the asymptotic kicks in at the same point, and these two together basically tells you that maximum spacing between operators in these intervals has to go to 0 as a function of j as fast as this number. So this is a subtle point. So I guess, so this thing is fine, right? It goes to 0. So it might happen that it goes to 0 and the asymptotic kicks in at some point. But if you go to a second interval, there the asymptotic kicks in at a different point. So it might happen that so suppose you have j star and 2j star, then it might, so here the spacing could be as j to the power minus 1/4, but then here on this interval, the spacing could be very large. Then you are screwed. So somehow you have to take the limit as in a uniform way. And this thing is coming from this statement that this error here, so whatever the error here, this error doesn't depend on the H star, where the center of the window. So the error is uniform in the H star, which basically means the asymptotic kicks in at the same point, irrespective of whether you're here or whether you're here. And because the asymptotic kicks in at the same point, and because you can shrink the window, that immediately tells you that the maximum spacing has to go to 0 as a function of j as fast as j to the power minus 1/4 plus epsilon. Okay. I guess this just comes from the error estimation. So Yeah, from that, from refined, and so we have to write down some bunch of terms and do things, and yeah. So I am basically hiding the details. Yeah. Yeah.
So does this say that within the menu, the error I made by using the right hand side is a same or
smaller in polynomial. Yeah, yeah, yeah. That's why the relative error goes to 0. Yeah. And this polynomial is related to having a polynomial window size, basically. So presumably you can imagine if somehow one can make this exponential, one can probably make this thing also exponentially small. That's like rough intuition. Yeah, yeah.
what controls that in the LHS?
Oh, this n can be anything, any number you pick. So that's another way of saying the fall off is faster than any polynomial. So
It's somehow it doesn't depend on H or whatever.
no, it doesn't depend on A star. Yeah, yeah. As long as A star is well, rather another way of saying it that as long as A star in some bounded interval, it doesn't depend on exactly where you are picking the A star. But if you let A star to infinity, then of course things will change. But then you are in a different regime. Yeah.
The right hand side is small or capital should make a difference.
Yeah, in this case, it should not make a difference because it's just, you can take any n. Yeah, yeah, exactly. Yes. No. Okay, very good. Okay. So, as I said, we basically go in this scenario. So here I slightly cheated because earlier I was talking about large energy, but here is not really in this direction large energy, but still it's very nice that we finally have a scenario where we can identify a class of CFTs for which the large spin spectrum is really dense. The maximum spacing for spin J operators with bounded twist, which basically means that in the age variable you have boundedness, it goes to 0 at least as fast as J to the power minus 1/4 plus epsilon. And of course, this will have implication. So this is about the density of states. You can go ahead and ask about matrix elements, like how the matrix elements of light operator behaves in a heavy operator and connect it to the ETH and all those sort of statements. But this is very, very nice because this is the first instance where we can concretely say that indeed the spacing goes to 0 and it goes as fast as this. And of course, from the holography, people expect that this would be exponential in minus square root j, but that's a long way to go. But we have been making progress over the years. So hopefully someday I will come here again and tell you a better result. I hope so. Yeah. Yeah.
We have a black hole system, atomic field theory, entities, and the entropy will go as
Yes.
log n, the number of states.
Yeah, yeah.
So if you have an exponential rising in the number of states,
Yes.
presumably in some
Mm-hmm.
then you would expect that the spacing goes exponential.
Yeah, that's that. So
Physics.
Yeah. But then you know that, as you well know, for example, in monster CFT, this doesn't work. In any rational conformal field theory, this intuition fails completely because everything gets.
Right.
Yeah.
I'm just having black holes in mind.
Yeah. So of course, yes, I completely yes. Yeah. Of course, I completely agree with you. Yes. Of course, yes. I completely agree with you that in the holographic setting or in this chaotic setting, you would expect. But but proving that is very hard and. Yeah. Of course. Yeah. I think that's the thing. Yes. Yeah.
You're proving this for any irrational.
Yeah, right now we are proving for any irrational CFTs, but I think this is probably a common philosophy in math also. Like you want to prove a theorem, you need to put in some information. You cannot just do things from like nothing. So here also in the holographic setting, probably extra information has to go in, and then the art is to figure out what that extra information would be and how to translate it into some statement that you want to make. For example, here just imagine, you just impose this twist gap. A single condition bought you a lot of things, all these powerful results. So, yeah.
And maybe to get even more powerful follow-ups, you need to put more other.
Yeah, that's definitely a possibility. Yeah, and that's what I think Ashok was suggesting for the holographic setting.
That's not ideas. That was estimate for it.
But for this case, you've been thinking about free boson, right? But there the number of primaries grow polynomial. Yeah, exactly. So, yeah, the only example I know where, so one negative thing about this setup is that there's no known example of this kind of CFTs, and there is one construction, like conjectural construction, where people take bunch of minimal models, of course in the minimum, and tensor it. Of course, you have a lot of higher spin currents. Then you turn on some relevant deformation by coupling them, and then you flow to a fixed point. And this fixed point has, and then people check whether this fixed point has these higher spin currents left, and it turns out they are all get lifted. So people expect this fixed point to be described by some irrational CFTs. So this is by paper by Connor, Behan, and Antonius. I don't know what exactly it is called. It's basically a bunch of minimal models deformed by some. So it's very recent paper. Yeah, in the large M limit. So basically you take. So you can always follow spins which are order 1 compared to M, but there is always this loophole that you cannot follow the spins order M.
So you have M number of minimal models.
No, this is M comma M plus 1. There's a left. And yeah, then you take 4 of them, and then you couple them by
the same.
If I remember correctly, yes, but I might be wrong. But that's the ballpark, roughly the idea. And then you do the perturbation in the large M limit. And then you can try that, like track the low-lying higher spin operators. They all get lifted. So I think these people have checked up to spin 12 or something.
So you do marginal deformation or relevant?
I think this is relevant, but it's like in the large M limit, you can compute the.
So in Gepler models, those also look at the spot symmetric versions. Okay, yeah, you have marginal.
Yeah, I think these are not marginal probably in this setup. And yeah, ordinary ones doesn't have. Yeah.
It's a modeling space.
Yeah. And
what was the discussion about the two scalar?
No, because two scalar have two variables.
yeah.
That is a high scale.
But it's irrational.
It's irrational, but it's not irrational, it's rational.
Yeah.
It's rational, yeah. Because they have two variables. Extra variable is there because once they C equal to 1, but
Yeah, C greater than 1 is important to have infinite number of Virasoro primaries. Yeah, otherwise A will vanish, and then basically the results will not hold. And also one more comment is that if you have higher spin currents and like more than Virasoro symmetry, then you can play the following game. Instead of imposing a twist gap with respect to the Virasoro, you impose a twist gap with respect to the extended current. And then you can play the same game. As a physicist, I would think that similar kind of results will hold. Maybe some factors will change. But again, proving that is a different ball game. But yeah.
That's not pure, right? Because, like for example, in the flat space, for example, there's a difference between having, spin 2 mass.
Yeah, that's true.
Just complete equivalence can.
Yeah, that's true.
It's not just a question of whatever you can do for.
Yeah, but I am saying at least you can write down a naive Cardy formula with the higher speed current. But then the detailed analysis, I would hope that it will go through, but unless someone does it explicitly, it's a bit hard to say. Yeah. Yeah, sure. Sure.
We want to two-dimensional normal field theory that
Mhm.
describes the DC system. This is D1, D5.
Yes.
Study nearly all.
Yes.
Now, we
Away
know
from
that,
the, yeah, they are marginal direction. Yeah.
normal,
Yeah.
somewhere in the marginal.
Yes.
Described.
Yes.
So now you're saying that suppose I take a very rapid piece of
Mhm.
black.
Mhm.
I think I can actually simulate that
Mhm.
the boundaries.
Mhm.
What I'm trying to say is that this method may apply.
Yes, this should be applicable in this setup. Yes. Yeah. Exactly. Yes. I guess even in
That, very
yeah. Exactly. I would think so. Yes, definitely. Yeah, it's going in that direction slowly, but maybe steadily. I would think. Okay, good. I guess I'm running out of time. Okay, we'll see how much we can do in the blackboard, but. Yeah, so I guess, yeah. So I. Don't worry, I will finish by 3:30 as I was. Yeah, and also I have to flight to catch. So. so. So for the rest, probably 25 minutes, I will just give you some intuition behind the proof and the sketch of the derivation. I already told you a lot of intuitions about when I explained the results. And well, just like whenever I say word rigorous, it basically means the errors of various estimations are bounded explicitly, as you can see from the results itself. So the intuition is following that about the proof is, okay, before going there, I guess I should write down. So this is the partition function. You basically expand it in the Boltzmann factor with some degeneracy which is positive. And as you all know, the modular invariance is basically swapping the space and time. So beta L, beta R becomes 4 pi square over beta L, 4 pi square over beta R. And there is a T modular invariance, which basically implies that H minus H bar are integers, so all the spins are integers. So now you can use the fact that this A is positive, which basically means that the Virasoro characters are universal, which has a 1 over Dedekind eta. So you can multiply with this Dedekind eta and write down a partition function only for primaries. So this, I have stripped off all the informations about the descendants from this, because at the end of the day, descendants are completely determined from primaries, so we don't care about them. So this is the vacuum module. You have these factors appears because they are null states, L minus 1 and L plus 1 annihilates. And then you have these primaries, which are excited states. And importantly, these both H and H bar are non-zero and greater than T gap. And because of, and earlier you have modular invariance, now have modular covariance. So if you take this partition function, under S transformation, it picks up this extra factor, which you can keep track of, which you can derive by using the modular transformation of the Dedekind eta. So
the script of the descendants.
Yes.
And you are saying that you still have modular invariance?
No, there is a modular covariance. Oh, because so ZV divided by Dedekind etas are the full partition function, and Dedekind eta. Yes, that's why C is greater than 1. Yes, exactly. Yes. Yeah, exactly. Yes. So basically, you start with this thing and you ask whether I can derive any formula by using this. Okay. So now just imagine that how do we do the Cardy formula? In Cardy formula, in the beta going to. Yes. So that's why there is these factors. Yes, exactly. Yeah. So you have to keep track of these factors separately. And in fact, as you know, in the dual channel, in the near extremal limit, this gives you some extra factor of this 3 over 2 log t. This 3 over 2 basically comes from this extra factor. Yes. So you have this modular invariance. And so now how do we use this to give you, again, I'm just trying to give you some intuition. So in the beta going to infinity limit, you know the vacuum dominates in this sum. So you have this expression, you do the modular invariance, in the beta going to 0 limit, you just change beta to 4 pi square over beta, you have this expression. So roughly speaking, what we say is that the high temperature captures the density of states at large energy. So you basically write down the crossing equation, basically the modular invariance equation. On this side, you say the vacuum dominates because beta goes to 0, this goes to infinity. And you ask that how this vacuum can be reproduced from this side. And in this side, you basically say the high energy states dominates. So this vacuum gets translated to some density of states for the high energy. So that's the usual definition of the Cardy formula. So you have two channels. In one channel, vacuum dominates. In the other channel, the high energy dominates. And you just go back and forth. So here I said that the density of states is inverse Laplace. The beta going to 0 limit should be understood on the complex plane. And the high temperature limit captures the density of states. So that's the usual Cardy formula, intuition behind the usual Cardy formula. Here you want to do large spin, which basically means h is large or h bar is large. That basically means either you take beta L to 0 or beta R to 0. So for the purpose of the talk, I will just consider on this limit. Again, you can go to just by swapping beta left and beta right. So the point is you want to understand the imposition, the implication of the modular invariance in this limit beta R going to 0. So as I said, now I will switch to Blackboard and I will see how much I can do. What are the chalks? I guess I could have done everything on the slides, but then at some point I got lazy typing the formulas. Oh, how to move that up? Or I can just move that thing. Oh wow, this is really fancy. Okay, let's see how much I can do. Okay, so we have this relation which is this chalk. Is it better? Okay, maybe I'll use this chalk. So we have this equation which is the invariance. So beta L, beta R. Then as I said, we want to understand this in the beta R going to 0 limit. So in the beta R going to 0 limit, I will have twice pi, beta R to the power half, and the vacuum will dominate from this side. So we'll have 4 pi square beta RA. And then there is a contribution coming from the null state, which completely drops out because the null state goes like 1 minus 4 pi square over beta R. So I can forget about it. And then there is a f of beta L, which is basically the same term with beta R replaced by beta L. And I keep everything on this side because I haven't taken any limit in the beta L. So that's the estimate in the beta R going to 0 limit, and it holds pointwise for every beta L. And now if you do the naive Cardy formula, what you do, you take this and you take this expression and you do an inverse Laplace. And when you do an inverse Laplace of this expression, you will get something like rho h comma h bar, roughly speaking, goes like rho of h0, rho 0 of h, rho 0 of h bar, where this rho 0 function is this cosine hyperbolic function I showed you. So the fact that the theta function pops up and it has support h over h minus a, it just comes from the inverse Laplace of this quantity. So you take this quantity f of beta L, you do an inverse Laplace, and you will see that the inverse Laplace only has a support over h bigger than a. And
right? So you have beta L.
yeah, but this expression is also symmetric, right?
Oh, that you're taking both beta L and beta R.
No. So beta r is 0. So this f of beta L is also the vacuum. So the point is there is a T gap. So in the dual channel, always vacuum dominates because of this presence of T gap. And intuitively, this is where the T gap comes in. Yeah. And that's why the formula is symmetric, but you should always. Yeah.
Once one of the betas go to 0,
Mm-hmm.
the other automatically behaves as if.
Yes, exactly. And of course, this is an intuitive argument. You need to show that this indeed happens, and that's where the T gap or downwards condition comes in. And so this immediately tells you that, like this kind of formula immediately tells you that rho j plus 2h goes like, so this is my physicist arrow sign, which basically means it's not precise, goes like this 1 over 2 square root j. So you basically treat rho 0 h bar, you replace h bar with j and take the j going to infinity. So cosine hyperbolic becomes exponential. So you get this formula 4 pi aj. Do not trust the factors because I like writing on from my memory. And then rho 0 h. But as I said that on this side you have a distribution, on this side you have a smooth function. So this formula doesn't make sense. So definitely this limit doesn't exist pointwise. So the next question you ask whether you need to do average over j and h. And so intuitively you would think that you need to average over both j and h because that's the intuition generally. But the fact you can use that this j is integers, you can use this fact to get rid of the j averaging. And you can make a statement which is valid for each j without averaging, and you only need to average over h. So let me briefly tell you how the thing goes. It might be a bit hard to follow within this 10 seconds, but I will still try. So the funny thing is that when we started this project, we did not really imagine that we could prove it for large J. So we basically initially proved some statements where we had both averaging over J and averaging over H. And only after proving that intermediate result, we realized that we can do much better. So in the paper, this middle part doesn't exist. Only the final part exists, but I want to show you the middle part because it has some advantage. Like it gives you some intuition why this final part exists. So instead of fixing on the particular spin, say we want to estimate rho h comma h bar, where I integrate h over some finite domain, and so say an h bar from 0 to capital H. dh, something like this. So here the h is integrated over some compactly supported place, and h bar is integrated from 0 to capital H. Capital H is some large number, and we want to understand this in the large H going to 0 limit. So as you average over h bar, that amounts to averaging over j. So this is not what we are after, like I showed you, but this is an intermediate step which gives you some intuition. No, this rho is, so yes, not quite, because this rho is the actual density of states. And the rho 0 is the Cardy formula, like the average rho 0. So you should distinguish between rho 0 and rho. Rho 0 is a smooth function, and rho is basically some Dirac delta distribution. So there is no cutoff. Yes, right. So now, and as I told you, this phi is a compactly supported function with a smooth compactly supported function. So you can go to the Fourier domain. So you can write it as ds. Let's see whether I can write it properly. Phi h. Yes.
How capital J is related to H star, which is the center of the.
No. So the thing is that so here I am doing from 0 to. Oh, this. So this. Sorry, this H and this H has nothing to do with each other.
Capital H can be much smaller than this.
No, this I will be deriving a formula for H going to infinity. Capital H going to infinity.
Capital H is
much bigger. Yes. Yeah. Yeah, but right now the formula I'm writing is true for any H, but at the end of the day I'm so this is the Fourier transform of phi, and then you have dH rho h bar e power minus beta plus is h dH bar 0 to capital H, something like this. So this is the phi tilde of S. So this is the Fourier transform. Yeah. So you should really think of this as H prime, some different variable. Yeah. Yeah. But then the point is that there are two DHs. So this.
And there is a relation.
Oh, sorry, I missed the H integral here. Yeah, I guess so. Think like this. So this is a function of H. I do a Fourier transform. This is this. And this is a function of H. It becomes phi tilde of S, which is this.
So from two integrals we can do.
Yes.
One of them will be the Fourier transform. Is that right?
Yes. So I am not. So you should. I am not touching the H bar integral. So you should think of this as a function of H. So the H bar integral is untouched.
Yeah, that is the last.
That is the last one.
Yeah.
And
why are there three? There is integral ds and then integral.
Oh, because we are doing a Fourier transform. So this is the definition of the Fourier transform.
So for both are doing that.
Yes. So it's like a convolution kind of thing. We are writing the multiplication in the convoluted form. Why?
Too many H's and it's getting confusing.
So think like this. So instead of D, let me write it down this way. Phi tilde S, F tilde S, ds. The definition of phi tilde S is this. Here yeah, but it's inside the integral. It doesn't matter, right?
See, convolution in H space. Sorry, product in H space and convolution in H space. How is it product in H space also? Yeah, exactly.
That basically comes from the fact that here e power is, so you can do this integral. So basically if you integrate over e power is h prime and Oh, yes, you need phi tilde of minus s, but you can make it symmetric. Yes, I agree. Yeah. So the point is, as long as you take a phi h to be, or you can take this integral from minus infinity to plus infinity. So yes. So this is not really the usual Fourier transform, because I am also integrating. There is a beta factor sitting here, which is basically I'm using the fact that phi h is compactly supported and smooth. So you're allowed to multiply with e power beta h prime and then take the Fourier.
Multiply, then you take it out.
Yeah, exactly. Yeah.
Okay, it's really, I would say it's like phi tilde of minus beta minus the s minus I beta.
Yes, you can say that, but the
Beta of plus minus s plus I.
yes, exactly. But the point is, this doesn't depend on beta because of analyticity. Yes, so I can choose any beta I want. Yes, exactly. Yes.
It's computationally you're moving. You can move from real axis to flat.
Yes. Yes, exactly. Yeah, and that's why I need all this infinitely smooth is all this thing. But the reason I am doing this would be clear now that the point is I want to understand this integral in the h going to infinity limit. But you can imagine that it's easy to figure out the h integral, the large h limit of this integral. So basically I have to exchange this s integral and the h integral using some dominated convergence theorem. And to use the dominated convergence theorem, I need a smooth fall off. So a nice fall off. Because I chose the phi h to be compactly supported, so this has a very nice fall off, and that means I can use the dominated convergence theorem and I can exchange the limits. And once I exchange the limit, I can pull this limit here. And now what is this? This is basically a
I is compactly supported. I mean, you are saying that the all derivatives are smooth.
Yeah.
But it's not an analytic function.
Sorry, I should not say analytic. Sorry, did I say analytic? Yeah. So yes. Sorry, I should not say analytic. It's a smooth function. Yeah. Yes. Yeah. Yes. You can still do that. Yeah. Or I guess better way to say it that you can multiply a e power beta h prime here and subtract it out here, and then phi h times e power beta h. This is again a compactly supported function with all these nice properties, and then you can Fourier transform. So in that way of thinking, you do not need to think of contour deformation. Yeah, and you're right. I should not say analytic. It's a smooth function, compactly supported, but it has essential singularities. Yeah. So anyway, so the point is that you can pull this integral, you can exchange this, you can pull this here. But now, see, this thing is kind of nice because this is kind of half inverse Laplace of the partition function with respect to h bar, right? Because the partition function is nothing but dh bar rho h comma h bar e power beta h, beta left h, beta right h bar. So I know how this thing behaves in the beta r going to 0 limit. So from that, there are like dedicated theorems like Tauberian theorems. So if I know this limit in the beta r going to 0 limit, I can immediately figure out this limit, at least for real beta L. So the steps are following. So first you start with this. You think of, let me write it this way, it is better. So you think of this part of the integral as a positive number for beta L positive. And you know in the beta r going to 0 limit, it has some behavior. Then you use these Tauberian theorems to say something about this growth when there is no IS. And note that you can only use Tauberian theorems when these things are positive because you are making sure there is no cancellation by the oscillations. So once you have this, so you prove a theorem for just for beta, and then you use the fact that this function is analytic on the right half plane. And then there are other theorems which tells you that if you know our analytic bounded function and if you know its limit on the real line, on the complex plane, it cannot just behave randomly. And that basically tells you how this function behaves when there is a S. And then you know this limit, you can exchange the things and you can prove a result for 0 to h. Now suppose you do not want to do 0 to h, you want to do for fixed spin. Then what do you have to do? You have to start with, instead of this thing, the full partition function, you basically project onto a fixed spin sector by doing a Fourier integral from minus pi to plus pi. And then basically you need to go through this whole procedure, but just by taking the partition function. So you start with this, let me write it down. I guess this is probably too quick, but anyway. So this is your fixed spin partition function, where basically you do a contour integral in a z variable and you go along the vertical line from minus pi to plus pi. And then you want to show that in a GA going to the infinity limit, this has a explicitly nice limit. And then you plug this in here, you again do some integration change, and then basically you estimate, instead of 0 to h, here you have rho j now. And to estimate this quantity, you divide it into two pieces. One is vacuum, one is non-vacuum. And non-vacuum can be divided into two pieces, where is h less than t. Sorry, what did I do? And h is greater than t less than a. So you show the vacuum term gives you whatever you want, the Cardy-like formula. And the non-vacuum term for finite s, you can estimate by using technique that we have been developing for last few years. And for large s, you use the fact that this has a nice fall off, and you exploit that fact to estimate the large s quantities. And once all the dust settles, you get the results like I just showed you. So
basically used to put bounds, right? I mean, you never make use of the non-vacuum terms actual.
Yeah, so the non-vacuum terms, you need to show the non-vacuum terms are suppressed. And then you also need to estimate how this is suppressed, because that controls the size of the window and so on. So
but you never actually make use of the fact, get an yes. You just want to show that they are suppressed.
Yes. So yes, so the only information that goes in from the non-vacuum stage is that it controls the size of the window. Size of the window. The fact that you can make it j to the power minus 1/4, not more than that or less than that, is tied with the fact that these non-vacuum terms are suppressed relative to the vacuum terms in some certain way. And that you can estimate. And
but you can't hold, for example, that the cost non-vacuum contribution comes from somewhere.
Yes.
You could make use of it actually to
yes, actually you can do probably better. Yes. Then yeah, I would think so. In our setup, so you should think of our setup as vacuum contribution gives you something universal, and all the non-vacuum terms are smeared with this phi. Yeah.
You have to be less than this.
Yeah.
Maybe with the non-vacuum, you can say J has to, the minimum gap has to be something.
Yeah, there is a possibility. Yes, I can see that. Yes. So yeah, so there would be some. The only worry I have that, so you have a non-vacuum piece. Let's take the first non-vacuum piece, and I think that if you do the inverse Laplace, then this inverse Laplace piece will be exponentially suppressed compared to the vacuum piece. But then you have other non-vacuum terms. But if we cannot improve the other non-vacuum terms from the polynomial suppression to the exponential suppression, there is no way we can make sense out of. So that's the only obstruction I can see.
This continuous integration of the Thomas integral over the chemical protection, going from minus alpha to alpha.
Yeah. Because spins are integers. So that's a very important ingredient. Yeah. Yeah, sorry, I think, I probably need another hour to explain all the details. I guess it's too quick. But also probably, I don't know, I also worry that you guys will get bored of all the inequalities if I start to show you. Yeah. So yeah, roughly speaking, that's the idea. So, and one philosophical lesson is beyond all this thing that oftentimes, so at the end of the day, when we use this, so here in this setup, basically you do something on the real line, you go to the complex plane by using some theorem, and then you do the dominated convergence theorem to move things. But here on this setup, in the actual setup, actually, we do not need to go through this real to the complex. We can actually do it on the complex plane. And one lesson is that if you can do some estimation without using any theorems, and if you can really do it, that always will give you a more powerful result. Because theorems always helps you to bypass some brute force nasty computation. But if you can do those nasty computation, probably you will gain much more information. Okay. With that, I will stop here. Thank you. In November, yeah. Yes. Okay, great.
Going for the first 2 weeks.
I'll be going for, actually, wait, I'm going for second and the bootstrap weeks. I don't remember.
So that's the second week bootstrap starts.
Yeah,
There's
there.
an extreme universe some.
Yeah.
So I'm there and then.
Okay, so we'll over. Okay, thank you.
So, where are you now?
I'm still at Caltech.
You're going to where?
I will.
Position.
Well, Siraj told me that they had the faculty voting and the faculty voting said yes, but then there are 2 more steps, some approval of some committee. So I hope that works out then.
I'm to go to IHS.
Yeah, in September, I'm planning to go to IHS.